Well, hello and welcome to the 38th lecture of this short course called Behavioral Theory of Systems with a View Towards Data Driven Control. So, in the last lecture we saw that in the last few lectures we found out that under this persistency of excitation condition, if you look at this H L W hat, the Hankel matrix created out of this finite time series data W hat, then if the input signal is persistently exciting of order L plus n plus 1, by which we mean that the Hankel matrix of L plus n L plus nth Hankel matrix of the input only, if this is full row rank, that is when we say that the input signal is persistently exciting, then in that case the column span of this guy would be equal to the L restricted behavior. That means all those trajectories restricted between 0 and L in the behavior. Yeah. And when this is true, and if L is bigger than or equal to the saturation point, then that would imply that I would just look at this H L W hat and I will find out its left kernel. Yeah, that will give me the MPUM of the data, right, and because of this condition, this MPUM will be representation of the behavior B itself. Okay. In the last lecture we also looked at a numerical method of finding out this left kernel. And instead of finding out just the left kernel, what we do is we look at this H L W hat. When all those other nice conditions about persistency of excitation and so on are satisfied, we look at this guy instead of directly calculating the left kernel of this by solving things like find out a vector V transpose so that this is equal to 0. Instead of this, what we do is we look at this H L W hat and find out its singular value decomposition, right. And then to get the left kernel of this guy, it is enough to look at say if you write U as U1 U2 dot 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 up to UR, then UR plus 1 dot 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 up to how many of them, how many rows do I have? This guy has rows equal to L plus 1 times Q, isn't it? Yeah. So, you take these vectors, right, and look at this U R plus 1 transpose and so on up to U L plus 1 times Q transpose. The row span of this is equal to left kernel of H L W hat. Yeah, that follows from singular value decomposition theory, and we just had a look about these things. We did not go into details, but we sort of gave ideas as to why this should be equal to the left kernel. And that is how in a roundabout way we find out the left kernel of this matrix that we wanted. But why did we do this? Because we said, because it turns out that singular value decomposition is such a nice tool, it is such a nice how do I say a way to compute these things, that the method itself, the method of SVD already has resistance or robustness to noise built into it. Why is that so? That happens essentially because of this fantastic property of singular value decomposition of giving us the low rank approximation. Now, the best possible low rank approximations of a given matrix. So, when there is noise, this W hat will no longer be the ground truth W hat, but rather a noisy W hat, and in that case the rank of this guy will in general be expected to be bigger than the rank of H L W, let me call O W original the original signal without the noise, yeah, will have lesser rank compared to this guy, because you see this guy, the rank of this guy tells us about the equations that it is satisfying. This rank is actually this matrix essentially is does not have as much rank as its number of rows, because there are these relations, right. Those are the vectors that we get in the left kernel. So these signals are satisfying some equations, so they have some order in it, whereas the noise is expected to be something which is random, and therefore it does not satisfy any equations per se. And that is why it is expected that those guys will almost be like inputs, and it will keep on increasing the size, the rank of this matrix A, the Hankel matrix HL. And that is why it is expected that the rank of this guy, the noisy data, the Hankel matrix created out of the noisy data, will be bigger than the rank of the Hankel matrix created out of the original ground truth data. So in that case, if I now look at this matrix, which I will not get this W0 hat, WO hat, right. This is not available to us, only this is available to us. So therefore, when we create the Hankel matrix, if I just blindly calculate its left kernel of this guy, that will depend on this rank, right, this untrue rank. This is the false rank that we get from the system, because this rank is falsely higher because the data is corrupted by noise. So therefore, if we construct this left kernel, as I said in the last lecture also, if I construct left kernel like this, then that left kernel will have too few equations, and also possibly erroneous equations because of the data, because of the noisy data. So what do we do then? What we do instead is we make an estimate of this guy. We estimate this number, the true rank, estimate the true rank. Yeah, we have some numbers to go by for this true rank, because we know that these numbers are things like L plus 1 times m plus n if L is beyond the saturation point. So that way we know these numbers, so we can get an estimate of these numbers if we have a priori knowledge about the system. So we have this guy, and what we do is, once again we do the SVD of HL, the noisy W hat. We do SVD like before, but instead of finding out the rank of this guy by looking at the non-zero singular values from this matrix sigma, instead of finding out left kernel like that, what we do is we once again look at the estimated true rank. Let me call that as RO. Oh, I should not use this symbol I have used before. What should I use here? Let me use D. Let me use DL. So we look at this number DL, which is the estimated true rank of the system. We may have to have physical knowledge about the system to know what this DL is. Yeah, it might not be easy to find out DL. There are other ways of finding out DL. I will tell you in short. Namely, this is the so called numerical rank of this Hankel matrix. Yeah, what is meant by numerical rank? You see, when this noise is there, if the noise has some bounds on it, yeah, like the noise is not too large, yeah, not too heavy in some sense, in that case you can see this, you can find out this expected rank by looking at these singular values. When you are writing down the singular values like this, yeah, you will see a stark difference between sigma d and sigma d plus 1, because ideally the rank should have been sigma d. So all these guys should have been strictly smaller than this guys should have been, so starting from these guys ideally it should have been 0 all of them, but because of the noise they are not 0. So they capture the effect of the noise, you know, the effect of purely the noise, not the signal. So therefore you see a you know what do I say, a striking jump between this and this, and from there you can estimate that okay, this must have been the rank. Yeah, these are all kind of heuristic ideas that I am giving, may not be, you know, I am not giving any physical or rather any proof for these statements, but that is how numerical algorithms really work. All right. So now without worrying too much about how do we get this estimated rank, so in other words I just say, suppose I know that this DL is the estimated true rank, estimated true rank of the matrix. What I do is, instead of finding out the left kernel by looking at, you know, the calculated rank R and looking at u R plus 1 dot 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 like that, calculating the, this will of course give me the left kernel of so R is calculated rank and DL is the estimated rank. So if I had gone by the calculated rank of HL itself, I would have said that okay, left kernel of HL W hat will be given by row span of u R plus 1 transpose up to u plus UL plus 1 times Q transpose like before. But I do not do this because this is wrong, this will not give me the system, because this is the outcome of the corrupted data, corrupted by noise. Instead what I do is I calculate approximate left kernel of HL W0 hat. How do I do this? This is magic, right, because I do not know this guy. How can I even expect to find an approximate left kernel? So I say that this approximate left kernel is given by the row span of this matrix. Instead of looking at u R plus 1, I will still look at u DL plus 1, the estimated true rank transpose and so on. U L plus 1 times Q transpose. I start from this number instead of this number. Yeah, why should this give me an approximate left kernel of the original data? Because I am going by the assumption that, you know, because first thing to notice is that this row span is indeed the left kernel of HL W hat, the corrupted data Hankel matrix from the corrupted data, its hat which is DL. What does this weird symbol mean? I mean by this HL W hat DL, this is the rank DL approximate, best possible approximate of HL W hat, you see, and this left kernel is given by the row span of the matrix that we constructed, R DL plus 1, sorry, not R, U DL plus 1 transpose dot 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 U L plus 1 times Q transpose. Okay, is it all right? Because this row span is the left kernel of this guy, and this is the approximated version of HL, where the rank is the expected or the estimated true rank of the data. That is why it is safe to say that this row span will give me an approximate row span of the original data for which the rank is equal to the expected rank. And this comes from the fact that when you do singular value decomposition, let me not write this, when you do singular value decomposition you get the best low rank approximation like this. Why did I write yeah, A hat. This is the low rank approximation from SVD. Yeah, following this idea, it follows that what I write, what I just wrote now, that this rank, this row span is the left kernel of this approximate, and that is why it is the approximate left kernel. Great. Yeah. So that is how with SVD you can do this identification or finding out this most powerful unfalsified model from finite time series data, even when there are even when the data is noisy. Okay. We stop here and we stop the discussion on finding out on doing this identification business here. In the remaining part of this course, what we will do is we will look at data driven control and three most important aspects of data driven control, and we will look at one example of each of these cases. Yeah, namely data driven simulation. Number 1, look at data driven simulation. We will look at data driven analysis, and we will look at data driven control. Yeah, 3 key aspects of data driven control. So without further delay, let me start with number 1. What we mean by data driven simulation? So data driven simulation, so what we have is, suppose we once again have a system, just a linear time invariant system given by the kind of kernel representations that we were talking about, given by a kernel representation. Sometimes it might also be given by an input state output representation. For the remaining portion of this course, we are going to assume that the state variables are available to us, but whenever the state variable is not available, you can look at the output and do do some sort of estimating the state, and from there one can proceed. I mean, what I mean to say here is that whatever we are going to see, we are going to assume that state variables are known to us, but when the state variables are not available to us, the ideas will not be directly applicable, but you can still derive ideas similar to the ones that we are going to see in the remaining part of this course, in the case when the state variables are not available, but only the input and output data are available. Okay. Now, so let us assume that we have this input state output representation, sigma x is equal to a x plus b u and y is equal to c x plus d u. In other words, I can also write x k plus 1 is equal to a times x k plus b times u k, y k is equal to c x k plus d u k. That is the description that we have, let us say, and from here we want data driven simulation. What do we mean by data driven simulation? Data driven simulation is this. Let's suppose I have data like this. I have data like so I have data like u0, u1. So u0, y0 data, this vector I know by measurement, u1, y1 I know, u2, y2 I know, dot 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 up to u. You can take t or t minus 1, does not really matter. Yeah, I write t because it is cumbersome to write t minus 1 all the time. So this is a finite time series input output data, finite time series input output data with us. So somebody now asks me, okay, u and y, a typical trajectory in the behavior. I want my information about u y restricted to 0 to L. Once again you can use L plus 1, does not really matter. Can I get this from this data itself? Yeah, that is the question. That is the question of simulation. That is it possible to simulate all possible trajectories restricted to this timeline from the measurements of input and output? Is it possible? Yeah. What do you think, when is it possible? We have actually seen a result which tells us that when this is possible, namely this is a sufficient condition for this is that if the input u, should I put a hat here? I think it is better to put a hat, because that this sort of distinguishes that these are my measured data and this is an arbitrary trajectory. So, yeah, one condition, one sufficient condition is that look at this h, look at this u hat. If u hat is persistently exciting of order n plus L plus 1, where n is the size of the state variable, this is because there is a minimal state space representation. I am also assuming controllability and observability is controllable, and this guy is observable. Okay. If u hat is persistently exciting of order n plus L plus 1, then we have this. Now, let us see why is this true, because if u hat is persistently exciting of order this, then notice that the following thing will happen. Let me write down some matrices. First of all, I write down this matrix. I write down u 0 x 0, right, u 1 x 1 dot 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 up to u L x L, and then I have u 1 x 1 u 2 x 2 dot 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 up to u L plus 1 x L plus 1. I am sure you can understand, you can make out what matrix I am writing out. I am actually writing out the Hankel matrix of Lth order with input and state data. So, this is u t minus L x t minus L, u t minus L plus 1 x t minus L plus 1 dot 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 u t x t. So, that is actually, and I should put hat here, yeah, because to distinguish that these guys are coming from the measured data. Okay. This is nothing but the Lth Hankel matrix created out of u hat x hat. You know, when we have persistency of excitation data, when we have u hat which is persistently exciting of this order, then from our fundamental lemma I know that this matrix with its column span will be u hat x hat will be the state space behavior, input state behavior, yeah, the behavior corresponding to the input and state, that is this equation, input state behavior restricted to L, yeah, by fundamental lemma, this is true. Okay. Now, I do a little bit of change here, little bit of permutation of these rows. So, if I do a little bit of permutation of these rows, then I can write this matrix down. So, a permutation of these rows of H L coming from u hat x hat actually gives me the following. I have Hankel matrix of order L coming from u hat and Hankel matrix of order L of x hat, but I will not write it like this. I am going to write this as x 0 x 1 dot 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 up to x t minus L. Okay. And then there will be x 1 here, x 2 here, dot 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 up to x t minus L plus 1, dot 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 dot, and you know what will come here, x L plus 1 dot 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 up to x t. That is what we will have. So, this is a permuted row permuted version of this guy, but what does this mean? Look at this thing now, look at this part now only. Because of this property, it means that for an arbitrary input u, an arbitrary input and arbitrary initial condition x 0, if we have these two, then you see this vector, look at this u 0, u 1 dot 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 up to u L and x 0, this guy can be an arbitrary vector of size, these are all of them are m size, yeah, and how many of them? L plus 1 of them. So, L plus 1 times m plus n. Okay. So, these many, so by choosing an input and an arbitrary initial condition, this can be chosen to be an arbitrary vector in R L plus 1 times m plus n. Now, because it's an input and a state initial condition, so this is in fact indeed u restricted to 0 L and x 0, yeah. So, this must be there in the column span of this matrix H L u hat and x 0 dot 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 up to x t minus L, yeah, and this is an arbitrary vector. You see, I can choose this thing to be arbitrary, this thing to be arbitrary, and still it will be there in this column span. Therefore, this column span must be a surjective operator, I mean this column span must be full this guy. So, therefore, the rank of this guy, so the rank of this matrix, that is column rank, but column rank is equal to row rank. So, the rank of this matrix must be equal to what? Must be equal to L plus 1 times m plus n, but how many? So, this is column rank of course, but that is equal to row rank, right. Row rank must be also equal to L plus 1 times m plus n, but how many rows are there? Count the rows, exactly L plus 1 times m and n. So, that means this matrix under persistency of excitation, this matrix here, this matrix is full row rank. We will give this matrix a name because it will be important for us in the sequel. So, what we have established, so give this name, we will call H L u hat to be equal to u, okay, 0 L t minus L. That is the new name that we are giving, right, and we will also call this x 0 dot 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 up to x t minus L, we will give this guy a name, we will call it x 0 t minus L. Okay. So, what we have established here is that if u hat is persistently exciting of order n plus L plus 1, then u 0 L t minus L x 0 t minus L, this matrix is full row rank. Okay. That is just a restatement of a fundamental lemma, it is derived from fundamental lemma, but this will be crucial for us. So, I think I have run out of time for today's lecture. So, remember why we are actually trying to do data driven simulation. We are trying to say that if we have a data like this, is it possible to get this information for an arbitrary trajectory in the behavior, by somehow from this data. Is it possible? So, it is like this question, we have this black box, we measure some input output data. So, we have information about a finite time series input output data, and from there we are trying to characterize all possible inputs and outputs, yeah, in the behavior, of course restricted to this 0 to L timeline. Yeah. What we have assumed is that this is persistently exciting of order n plus L plus 1, and that tells us that this matrix is full row rank. What do we do with this full row rank property and how can we do data driven simulation out of that is something that we will see in the next lecture, and of course we will also see one example each from these two other cases, namely data driven analysis and data driven control. Okay. So, that we will see in the next two lectures. Till then, take care of yourselves. Bye.